server. And if you haven't already, please join and message me or send me a friend request so I grant you access to the channels. I really want to see you guys on the server, so please, if you have any errors while you're writing your code, or if you have any questions during the lecture, feel free to post them on the discussions forum, and we'll pick them up. And yeah, my second announcement is every Thursday we'll be going out for drinks after the lecture, so feel free to join us. And the last Thursday,
or 2 or 3. So if anyone's a PhD student or postdoc, just please approach me after the session.
Cool. Or knows anybody who might be able to do that. Great, yeah.
Yeah.
We need a responsible adult in all the sessions, apparently. Okay, cool. So that's it. So let's get started. So that's all good. I got a new streaming setup today, so we just need to make sure that's all working. All right. So welcome, session 2. Here we are. Today, picking up from where we left off yesterday, trying to go cover a lot of ground quite quickly. Yesterday, the aim was to bring everybody up to scratch on the essential machine learning concepts. Today, we aim to understand PyTorch. That is the goal. Basically, for the rest of the entire program, we're going to be using PyTorch heavily. It's a Python library that's going to help us build all of these deep learning models. And so it's really important to understand it. So today, we're playing around with that a lot, giving you guys a bunch of time to program with that and help out wherever I can. Was there any questions or issues about the stuff we covered yesterday, stuff we want to dive into now, or should we get straight into it? Question.
yeah, we just didn't go through the underfit and overfit models at the end yesterday.
Yeah. Okay, cool. We can take a look at that very quickly now. So just one thing to start here in lesson 1 in the end. One thing we didn't talk about is the difference between these two things. Well, the first one, underfit models, which is where you essentially have a model. It doesn't have enough capacity to fit the shape which you need it to fit. So you can see here on the left, the true data is the crosses and your predictions is the straight line. This doesn't model the data very well. So it doesn't capture the relationship accurately. And if you give it some examples, especially in the middle, something like that, then it's going to predict something which is very wrong, just because it doesn't capture that curve in the actual generated data. And on the right-hand side, you can see what the loss curve for that looks like. So you start off with a random model. It's very bad, as always, and you adjust it step by step, changing the steepness and the vertical intercept there, and it gets better and better, but it doesn't get good enough. So you're way off where you need to be. That blue is the acceptable loss down there on the right-hand side, and we're already down to here. So this is the kind of thing, this loss curve, you can look at this and use it to diagnose what might be the issues with your model. And this kind of a curve, it gives you an indication that the model might be underfit. The other bugs as well, but this is what that shows. This is useful because you have all of this data. You don't have this data necessarily, partly because one, your input data may be very high dimensional. Imagine you're working with even the very simple house pricing data set, which has 9 features. That means this is not 1-dimensional axis, it's a 9-dimensional axis. Now where it gets very hard, so you can't interpret, you can't visualize what that actually looks like. So this thing is very hard to understand. The other case is that you're predicting on data where you don't have labels, so you don't know where the output should be anyway. Although you wouldn't know the loss for unseen examples anyway. So that's underfitting, one particular problem that you can get when trying to build these models to represent the relationship between the inputs and the outputs that you have in your data set. The other side of that, as Ahmed mentioned, is overfitting, which looks like this. So this is where you have a model which is kind of has too much capacity. It can represent these crazy input-output functions. As you can see, it has them on the left, and it's scored perfectly on the training set data, the orange data points. It passes through all of them almost perfectly. But then on unseen data, it doesn't capture the relationship at all because it's been overfit to the training data. So the loss curve looks something like this. And now on the right, you've got these two loss curves, one being the training set, which goes down as you expect and reaches below this acceptable loss threshold, and the validation set loss, which doesn't go down far enough. So remember, the validation set loss is to see how it generalizes to unseen examples and choose between different models you trained. And so problem here is that it's not going to generalize very well, and you can see that from these loss curves. It fits the training set data very well. It learns to get very close to the examples it's already seen, but it doesn't generalize. And so this loss curve on the right-hand side here can show the symptoms of that and help you to debug that. All right, any questions you want to jump into that? Cool, should be familiar enough. And today, we're going to jump into this notebook. So if you want to open this up, feel free to go through alongside or just look up at the front. Understanding PyTorch. So we talked a lot about these machine learning models yesterday, and I've got an example straight away of how you might implement one in PyTorch. This is a trivial implementation written in pretty much just raw Python and NumPy. And as we go through this notebook, we'll learn how to replace this with a much better way to do it, and I'll explain why in a second. So you can see here, just to run over this, what's happening. Is that big enough? Zoom in, zoom out, zoom in a tad. So there you can see I've got this class linear regression. It means I can make instances of that class. And in that, I've defined 3 different methods. So this linear regression class, it can do 3 things. This is the initializer, which runs when I initialize it, like that, with those round brackets on the end. Takes in those 2 parameters, number of inputs and number of outputs. And when it initializes, as soon as the model initializes, it needs to do some things. In this case, this model needs to set its initial weights and its initial bias, which are 2 parameters of this model. This linear regression model just represents a straight line. And so the equation here, which it uses to make predictions, is simply wx plus b, essentially. Multiply each of the features by an associated weight, and then add some constant value. That's just the straight line equation. And that's how it makes predictions. We'll talk a lot more about that next, so don't worry too much about the linear model. It's just a good example to show about how PyTorch works in a second. So the key thing in this code is the third function down here, which is getGradients. This is a function which returns you the values of how steeply the prediction will change as you change the different parameters. Again, I just asked some mathematician for these values and he told me them and I wrote them in the code, and that's fine. But the problem is that I actually had to know them and I had to write them. Why do we need the gradients? Anybody tell me? Why do we need the gradients of the model?
Which direction we want to move to minimize the error.
Exactly, yeah. So we want to have this value, which is the loss. I want to reduce that. I basically want to look at what's the most downhill direction of that curve, and I want to move the parameters in that direction such that the loss reduces. So I need to know the gradient of the loss with respect to the different parameters, and this here is actually the gradient of the predictions with respect to the parameters, but we'll join that all together later. The key thing is to understand here, with this implementation, I had to actually know and write out the equations for the gradients. So down here, just an example of how you might use that. I've got the model there, create some fake data, predict it, get the gradients, and if I run that, we'll let the notebook start and see the output there. Give it a second. Cool, so there's the predictions. I've got 2 data points, so it made 2 predictions. I've got the weight gradient and the bias gradient for each of those predictions. So moving on to the more important part. Just firstly, this is kind of what's happening here. I showed this diagram yesterday, but this is what the equation looks like for the linear regression model. It's a straight line. relationship between the inputs and the predictions. And you can see how the shape changes as you change the parameters on the right-hand side. So as the bias goes up and down on the vertical axis, that changes the y-intercept of the prediction. And as the weight changes, it changes the steepness. Higher weight or steeper. Again, we'll talk about that in a lot more detail tomorrow. But the idea is we just got to find these parameters on the right-hand side. Find the right parameters, and then the input-output relationship looks correct. Very simple model still on the left-hand side, but we'll make it more complex as we go. But it's a key building block. So to find good enough parameters, we use gradient descent. And to show 3 graphs at once, you can kind of see 3 different ways to represent what's happening here. On the very left-hand side, this is the hypothesis, you might call it. It's the relationship between your inputs and your outputs. Again, very hard to visualize for a lot of useful problems. This is a trivial case where you've got a scalar input and a scalar target. The real data, the process, and you have this model, the green line, which you want to fit to that data. So it's changing and it gets better. Next thing is the loss surface. So the loss surface is a vertical height above every possible parameterization on the XY axis there, round 1, round 2 axis. These might be the weights and the biases. Different values of those. They have a different loss, which is the vertical position on that surface. And you can see here, this is the visualization of gradient descent. Start at the top, and the ball effectively rolls down to the bottom. And when it's at a low point, hopefully a suitable minima, then your model's got better. And the third thing shown on the right-hand side over here is how the loss curve changes over time. So this loss represents the same thing as the middle graph, the vertical height, and it's just a measure here of how does that change over time, right? As you take more updates, you make more updates to the model parameters, as we're doing in the middle graph, step by step, you can see the loss goes down because the model gets better, which is what's happening on the left. So that should be a good overview of how how in general these models work. You can think about those 3 graphs happening at the same time. The hypothesis, the loss surface, and the loss curve. So the problem with the implementation above, with that, when we're doing all of this, is that you have to, firstly, linear regression only models very trivial problems. So on the left-hand side, trivial problem, scalar input, scalar target. And an interesting problem is going to look like some crazy relationship between the inputs and the outputs. You know, what's the relationship between the pixel values in an image and what the classification of that image is? Very complicated input-output function. And to make it much more complicated, this might be happening in a million dimensional space, right? If you've got 1,000 by 1,000 pixel image, that's a million pixels. It's a million features, so your input space is a million dimensional. So you cannot visualize this thing. So it gets very complicated very quickly, and it's going to be very hard to fit with a linear model, which means, of course, you need more complicated models. You need models which can represent these kind of crazy functions in very high dimensional space. So that's fine, we could code them up. But if we want to train them in the same way, that means that you need to be able to find the gradients of the loss with respect to each of the model parameters. And then it gets very complicated because you have to, ask a mathematician, okay, how do I calculate that thing? It's a huge model. There's, 1,000 different transformations happening. And then you write one bug in one line. You don't know where it is because it all computes, but it's just the wrong number. So it gets very complicated, and it's very easy to waste a lot of time doing that and screw it up at the end. So you need a way to not have to write out those gradients, okay? And that, I cannot be more clear, that is the point of PyTorch. That's what it does. It allows you to write the models like we saw the first block of code, but not have to write the gradient function. So to scroll down and show you that, this is the implementation in PyTorch. I'll break it down a bit. So similarly, you've got a class. It's just a blueprint for a type of model which you want to use. We've got this initializer, and this one, it just creates its single linear layer. This is the thing we'll talk about a lot more next lesson. But this is basically just something that you can call on your data, and it does the wx plus b equation. So that's what we return from this method down here. We'll talk more about this in a second, but it's called forward, not predict, because PyTorch defines what happens when you call the model on some data as what's defined in the forward function. But the important point of all of this code here is this line. There's no need to implement get gradients. Under the hood, PyTorch can do that for us. So, in this case, how many lines have I saved thus? I've saved thus only 4 lines. Could have done it in 1, but I've saved us that line of code. And in the complicated case, this could be unwritable, basically. Because you need to calculate all those gradients, and you need to make sure your maths is right when you do it. So, aside from that, there's a few key differences which I want to talk through here. Some things which I skipped over there. The first one is that the model inherits from this class called torch.nn.module. That's important for all PyTorch models. And it does a bunch of useful stuff under the hood. Some of it we'll kind of run into later. Some of it is useful to think about now. And one of those things, which I just alluded to, is the fact that every class which inherits from torch.nn.module, when you call it on some data like that, it's going to run the forward method. So this one's just a little nicety. That means you don't have to write model.predict all the time. You just can use it like a mathematical function. F of x is essentially what you're writing there. But it also means that PyTorch can do stuff in between what you define in here. Maybe some stuff before, some stuff after. It can track things and that sort of stuff. So there are other key things which torch.nn.module does. Yeah, we will get into that, but maybe another thing which you want to know about is that it stores the parameters of any other transformation building block inside the model as parameters of this model, which makes them easy to access later when we want to optimize this model. When we want to optimize it, we need to know what parameters you want to change, and you can get them very easily by doing something like this. Okay? That method, not something I defined in here, it's something inherited from this class. So this class has all the definitions of the different methods, which are really useful for machine learning models. To run through a few others, some models behave differently whether you're evaluating them or training them. Sometimes you want to switch back to training mode. All these things are defined by torch.nn.module. What else is useful in there? A bunch of useful stuff. As I said, we'll figure it out when we come to it. But basically, there's a lot of useful stuff under the hood. It comes from torch.nn.module. So, yeah, another important thing to note here is instead of defining parameters, we've actually defined an attribute of a class that represents the transformation. It's done using class from PyTorch, and it's this layer here, the nn.linear layer. So this contains all of the parameters now. Previously, we said something like self.weight equals numpy array, self.bias equals numpy array. And here, instead, you've just basically said the attribute is one of the transformations, this linear transformation. And as I mentioned earlier, that's something you can call on your data to apply that transformation, basically. So torch.nn, the neural networks module of Torch, contains all kinds of useful transformations, which we will get into later. You might have heard of convolutions or attention or dropout or those kind of things. Again, very complicated to implement yourself mathematically, easy to do inefficiently or incorrectly, and PyTorch has all of them off the shelf. So that's what comes with PyTorch. I'll pause for a second and take a drink and have a think about questions you have about that code. Feel free to shout out. Anything at all unclear about that? Because I'm going to make you write one later. Yeah.
What is a super do?
Good question. Yeah. So question, what does the super do? Anybody have an idea of what the super does?
Storing program lines, calling some kind of parent class or something.
That's basically what it's doing. So what does the super method do? Or what does a super function do? It's a built-in function to Python. Super gets you all of the methods and attributes from the parent class. So super returns you this object, and from it you can access all of the methods and attributes of the parent class, including in it. Is there a question over there? Is there a question there? No, we're good.
But if I didn't have it, then one couldn't write this for
Sorry?
I didn't write the super topic, like a super
Yeah.
I couldn't define this.
Exactly, yeah. Because things like everything I mentioned there, the fact that forward implements the call, the fact that you can do .eval and .train, all of that comes from torch.enn and .module being initialized. And so the point of this here is to initialize or call the initializer of the parent class. Cool, great question.
If you inherited more than one.
That's a topic for a different day. Multiple inheritance, don't worry about it for now. But basically, this is a class that contains a bunch of useful stuff, and this just makes sure all of that's initialized correctly. If you don't have that, you'll get an error, which is a very common error. It will say something like this: cannot assign module before module.init call. And this is raised by torch.enn.module because it wants to make sure if you're defining building block transformations inside the class, it needs to know about them because it needs to know what the parameters of this model are.
And what would be the difference between like torch and n?
Mhm.
Just without the module in the end.
Yeah. So torch.nn, you can think about this. This is a big folder. This is a file. This is a class inside a file.
Okay.
Yeah. So this is just a folder, and in there, there's a bunch of useful things, including the definition of the linear class, for example. Dalia.
So just really quickly, you're calling that class, and obviously that class is something that exists, someone else wrote it.
Are you talking about this line?
Sorry, no, above, like class PyTorch block. So this is,
This one.
yeah, this. So you're telling it, go to PyTorch linear regression, find me this module, and then inside it, you're like defining things and calling like the elements of them. So like linear layer is, for example, something that exists in that like module, etc.
Yeah, basically. So this is a custom name, which I've defined myself, PyTorch linear regression, and call it whatever I want. This is a class somewhere else, which, it contains its own definitions of methods and that sort of stuff. And all of those are now kind of stacked into this model as well. So, there's another method here, which is like the parameters, as I showed, and that comes from the definition here. It just inherits all of them.
Makes sense.
Cool. Any questions about that? Great questions. Cool. So where are the parameters is the first question. Well, I said they're in the transformation. They're in that linear layer. So I defined in my model an attribute called linear layer, and that itself, like everything in Python, is an object which has its own attributes. In this case, it's got an attribute called weight and an attribute called bias. So if I run this cell after defining that model, and I need to run it again above because I didn't run it with a super. I run that, this works, scroll down here, run this, and now you can see printed the values of the weight and the bias. And so those are the initial values, initially randomized values. Cool. So that's where you get the actual values of the weight and the bias from, which you might want to look at later. They might tell you something about what's important to your model, what features have high weights, low weights, what the bias is, etc. And then the next question, now we know where the parameters are, is where are the gradients? Where are the gradients? Well, to start with, they don't exist because we haven't calculated them. So we need to go through that process firstly. This is me doing that. So I've got some input data here. It's just a single example with 3 features, and I've got a label for it, just a scalar value. I initialize my model, tell it I've got 3 inputs and 1 output, and then I call the model on that data to make a prediction. At the end of that, I calculate the loss. So once I've done that, I get this. I don't need that line really, but we get this loss, and this is the thing which we want to figure out what's the rate of change of this loss with respect to the parameters. So this is this value here actually represents our current height on the loss surface, just a single point on that surface that we showed earlier. Where are we? And what we want to know is how steep is this? How steeply does this change as I change each of my model parameters? Under the hood, we've got 4 parameters now, but this will work exactly the same way if I had 175 billion. So to get those values, the rate of change of the loss with respect to the model parameters, you just call whatever you've got dot backward. That should probably be loss dot backward actually. So if I run loss dot backward now, nothing happens apparently. But under the hood, this has happened. So what is this? Firstly, this is the graphical model of the linear regression model, which is all this spot on the left-hand side there, and the evaluated loss on the right-hand side there. So you might see a lot of these diagrams as we go forward, and if they're not clear at any point, feel free to stop me and let me know. But simply, from the left, I've got some input features x, I've got a weight, I multiply them together, get this xw, I add this constant offset, so that's the y equals mx plus b equation there, that's my prediction. Then I've got a label, I combine that with the loss using the mean squared error to calculate, with the prediction, to calculate the loss using the mean squared error. And that's the final value, which is like, how bad is the model right now? Given that, I want to go backward and figure out what's the rate of change of the loss with respect to every different thing in this graph until I can calculate how it changes with respect to the things that I actually care about, like my weight and my bias. Because these are the things that I want to optimize using the gradient. So you may be aware of the chain rule, which is that if you have a series of transformations and you want to know how the input to that series of transformations affects the output, you can multiply their gradients together to get that final value. And that's the value that we want. We want to multiply this by this by this to get how the loss changes as we change W. That's basically a direction of what's the most uphill direction. And then we want to move in the opposite direction of that for all the values in there. Cool. Questions about the computational graph?
I'm sorry. So you initialize the values for x and y by PyTorch.tensor, but what were those?
So those are, so that's just a dummy example. Really, you get them from your data set. So that's like the raw data you've collected from, whatever process, from taking pictures and manually labeling them, or, experiment measurements, that kind of thing. Cool, great. So important graph, make sure you understand it. That's how we calculate the rate of change of the loss with respect to the parameters of the model. All right. So there's a few details of this dot backward method, right? One of them is which tensors get their gradients populated. Not all of them. It's not all of them that get their gradient populated. Why is that? Well, it's because we don't need the gradient for some of them. For example, I don't need to know how the loss changes as I change x or y, simply because I can't change those things. I got them from nature, from taking pictures and labeling with their classification. So I don't really need their gradient. And if I did compute it, it would just be wasted compute, wasted time, wasted space. So there is a flag which is set for all different kind of for all PyTorch tensors, which is the requires grad attribute. And that tells PyTorch, should I calculate the gradient of this thing when I do dot backward or not? It does this recursively. So it'll kind of look at, okay, what did I call dot backward on? Which of those things have requires grad equal true? This one doesn't, so I don't calculate its gradient. This one does, so I do. And then it will go recursively and do the same thing again. Okay, both of these have requires grad equal true. Calculate their gradient, and then look on this one. Okay, this one doesn't have requires grad equal true. This one does. So down here, you can print those values, right? So we've got input data. We've got the model's linear layer weights, we've got the model's linear layer bias, and we've got the prediction. The first three are probably obvious, as I've said. We don't need the gradient of our input. We do need the gradient of our weight, and we do need the gradient of our bias. But we do actually get the prediction has requires grad equals true. Why is that? Anyone understand, Dalia?
Because of the chain rule, I think you couldn't calculate the weight and the bias gradients, which is what we want to update the model if you didn't get the gradient.
Exactly, yeah. We couldn't calculate the gradient of these if we don't calculate this one. So anything that's produced from a tensor which has requires grad equal true also has to have requires grad equal true. So whatever variable this is stored in, it will have requires grad equal true, same for this one, and so on. Cool. So that's the first detail of when you call dot backward on anything that's been computed from other tensors. It's the fact that only some of them get their gradients populated. So you can see that here. I've kind of tried to highlight what's going on. The purple ones are requires grad equal true because they're computed from a node which has requires grad equal true, and the blue ones requires grad equals false, and the green ones, which we didn't set, by the way. Remember, they were just initialized by PyTorch when we created that linear layer. They have requires grad equals. Sorry, that should be true. That should be the other way around. Yeah, the green should be blue. Thank you. Awesome. So the next detail is what are the values which actually go into there. It seems like we already seem to understand this, and I think did a pretty good job of getting through it there. But it's not the common mistake is to think that the grad is just, sorry if I go back here, the gradient that ends up there is just this thing. So what's the dot grad attribute, which gets stored in here, which is where we store the gradients? Every tensor has a dot grad attribute. That value is not populated by this. It's populated by the multiplication of this and this and this. So PyTorch not only calculates the gradients between each different transformation, but also multiplies them together from the thing you call dot backward on, in our case our loss, and the things which you have, the things which you want the gradients of, which is everything which has requires grad equal true. So when it fills in the dot grad value, it will multiply all those gradients together. So at the end of the day, it's done the gradient calculations and the chain rule for you. Really nice, right? Really nice. Much easier than having to do it by hand. I've run this before and made people do it by hand, but I don't think it's worth it. So we'll get straight onto this. This is a graph I've got here to illustrate the point that a lot of the code inside PyTorch is people writing functions which define how you calculate the gradient. So PyTorch in the torch.nm module has all these transformations, like I said, linear and dropout and convolution and everything like that. And all of them have an associated gradient function, which is, okay, if I have a certain input, how steep is the input at that point? And a lot of the code in PyTorch is actually just defining those things. So PyTorch gets it, and PyTorch stores it in each variable in this grad function attribute. So down here, I've got a bunch of different things from my input. Just a bunch of different variables, right? I've got my inputs, my model parameters, and my prediction. And now I'm printing their grad function. So let's take a look at what that gives us. The grad function for the inputs, the weights, and the bias is none, because they were just loaded in or initialized randomly. They didn't come from any function. But the prediction, it came from something called add backward 0. So this is basically the function which created the prediction. And PyTorch stores that. So as you compute things, PyTorch on the fly creates this graph and builds it up, storing not only the values, but also the relationships between the values, so that when you call dot backward on anything, it knows what function to use to get the gradient. Every tensor that's computed has that associated gradient function. It's like, okay, if the input was this value, how steep was the output changing at that point? So just to highlight what the gradient function is again for anybody who's not totally aware of that. So on the left-hand side, we've got some functions. You can see this green one, for example, it's a straight line, has constant steepness everywhere. So whatever the input is, it's increasing at the same rate. It's so steep. And on the right here, you can see that the corresponding gradient function is just a flat line, because the gradient's always constant. This orange one, okay, it's very steep in the middle, and it's flat on either end. So the gradient function looks like this. It's flat, it's 0 on either end, 0 steepness, but it's got a high gradient in the middle. And this quadratic one on the left, it's steep on either end. On the left hand side going down very steeply, on the right hand side going up very steeply. And so the corresponding gradient function looks like this. In the middle, it's flat, the 0 gradient. On the left hand side, very negative gradient, going downhill very quickly. and on the right hand side going up. Very good. So any tensor that's created in PyTorch stores how it was created. And then when you call dot backward, it just looks at that function and says, okay, well, how steep was it at that point? And that is the value. That is this value, which gets stored in the dot grad attribute of a tensor. Do I have that here? Well, if you print any tensor dot grad, it'll give you the current value of the gradient. I think I had that. No, we didn't have that anywhere. But once we call dot backward on something, as we've done above, then you can do, let's do prediction dot backward. Sorry, prediction dot grad. And you can see, what can you see there? The dot grad attribute that is not a,
Does it not need
So-
brackets or others?
this dot grad?
Yeah.
No, because it's an attribute, not a method.
All right.
So it's not a function which you can call, it's just it's a value. In this case, the value is none. It hasn't been populated yet. If we do maybe prediction dot backward, and then run that, it says, okay, grad can implicitly be created only for scalar outputs, because it just gets complicated if you're trying to do it in a vector. So let's do, did we have the loss yet? We had some loss, right? So we do loss dot backward, and then we can do loss dot grad. See which error we get this time. I've already tried to go backward through the graph, and it says here, saved intermediate values of the graph are freed when you call dot backward. So if you want to do that, do this thing. Doesn't really matter. We just need to calculate it again. So let's go back up here. Here's where we calculate the loss. Okay, I've calculated a new loss. Go back down to my code. Run loss dot backward. The loss dot backward, I printed loss dot grad. It was none. But if I print model dot linear layer dot weight dot grad, let's have a look at what that is now. You can see that's been populated by these values. So that's like how steeply does the loss change for each of those different parameters. Now, they've been stored in that parameters.grad attribute. And so this basically tells us if I move this parameter in the negative direction, the loss is going to go up. That's because this is negative, right? Just see that this is, if I increase this parameter by 1, the loss is going to go up by -10. So what I want to do is move the parameter in the direction which is going to decrease the loss. So I want to move in the positive direction. And the same for all the other weights, right? They each have an associated gradient. It's how the loss is going to change. I'll let you guys get hands-on with that in a second, but you can imagine the same is true for the bias. So I've got a scalar value there, which is how steeply is the loss changing at this current value. And for every intermediate value in this graph as well, you'll have those dot grad attributes. All right, cool. So I think now is probably a good time to jump into some practicals and explore some of those attributes that we've just looked at, right? So check out the first practical here. We'll do this for 10, maybe we'll do it for 15 minutes and make sure you get a chance to play around with it. But basically, yeah, create a variable, assign it to a value, convert it to a torch tensor, set it to requires grad, compute a new value y from it, and then look at their grad values before and after you call dot backward, have a play around with those things. So key things to understand at this point is the requires grad equals true, backward, and the grad attribute. So take 10-15 minutes to do that, and then we'll jump back in. You won yesterday. Okay. Well, PyTorch is the short answer doesn't really matter. Doesn't matter PyTorch is supposed to have a dynamic graph where it's built on the fly, like I said. So you don't have to kind of call it back and build the graph for me. So like values, and then it just was very actively used for just things like together, multiplying things, all this without having to. But it's a technical detail that doesn't really matter because that's very popular. I think PyTorch is even more popular now. At least in the need of research. Yeah. Cool. That's an excellent question.
Just 1 second.
That's what I did, but it still says false. Yeah. Oh. Okay, now it's not.
Yes, that happens for practice and don't have
Yeah, so I just. So basically, you have to, so you just, so like you have to do that content. Now you talk about the data.
Ah, crap.
And the rank 1, 2, 3.
No, alright, we're good.
Watch here, okay. Here. So like if you're like 5, 4 steps are here, they just give numbers. And you tell it data type is exploded.
Gradients. Exactly. Yeah. So if you have a usually call it on the optimizer. I'm not sure if you can call it on the tensor here, but there's a thing mentioned 0 grad here. All it does is it sets the gradients back to none. Why is that? Exactly, yeah, for the next iteration of the model. So we want to get the gradients not just once, we make one prediction, but we want to make a prediction, calculate the loss, get the gradients, and then update the parameters just a little bit, and then do that many times. So every time we go through that series of steps, you want to zero the gradients back again, because once you move them, what's in the .grad attribute, the gradients, is stale. So you want to get rid of it. So that's what 0 grad does. For anybody wondering, I just had a few people say that, so there you go. You keep going on. How do you call it? In this practical, it says you can call it on the tensor. You should check that for me, but you usually call it on the optimizer. So I'll show you that whole example in a second. But essentially, you do, okay, predictions equals model colon x, calculate the loss, and then do loss or backward, have optimizer, and then update the parameters of the optimizer, and then do optimizer.0 grad. That will look at all the parameters it tracks and set them back to 0. I'll show you that in a second. Yes.
More of the
It doesn't work.
yeah.
Yeah, it's
Yeah, I think that's a mistake.
yeah, and then object has an attribute in order.
What does it say if you set that by
Oh, I guess yeah.
Yeah, it just says, it just talks about the so it might be that, yeah. Because we're doing it semi-manually.
Yeah. You could do it totally manually. You could do it by saying grad equals up. But that's what's happening behind the scenes when you do certain grads. Yeah.
Yeah, so I think I just went through what I'm asking. However, not that's
Yeah, so if you do this one, what do you get? Well, so your graph just looks like this. Maybe it's they're not connected. And actually, even though this one has required grad attribute, we've done dot backwards on this one. That would populate its own grad attribute. But not this one, because they're not connected. If you had something like this, a made-up equation, whatever, stuff like plus x, and did that dot backward, then it would populate both of their dot grads. Because it's created from those two things. If they have required so that's y dot grad. So that is
Other people are going to say.
oh sorry, I take it back. Yeah, so yours are connected. I thought you were defining them separately. So you have You have that, right? What you've done is you've created y before you set the grants. So before this one, x has requires grants by default because you created it. So here, when you create y from it, it's not no reason to have requires grants. Yeah. So if you set requires grants true exactly there, then you should see y dot requires grants. Yeah. Where is the y? Yeah, that's exactly. That should be a line one. So what happens here, right? Stop. X has required values. And then you create something new for it, and that thing also has. So you just missed out the actual in order to do this, this requires yeah. So two things there going on. So that's a good one you thought. And then the other one is the one I was saying is basically if your x doesn't have requires right, any greater than is by default so you have requires right.
Just call it requires
All right.
I have a question. That's the teaching note, okay?
Yeah.
You go to the very first ever taught things. Right, here, when you go to define project, you go return x at self weights. I don't understand that, I've never seen it before. What's that mean when you go to add?
That, yeah. I didn't know this for ages either. It just means a matrix multiplication.
Oh, okay.
Yeah.
That's so cheating.
How nice is that? Yeah. But otherwise it can default to a dot product. So this is the way to specify that in NumPy.
So I did my machine learning in math.
Of course you do. Of course you do.
Okay, that's fine. Yes, that's the thing that's broken, I think. Yeah, I think it's about you're only working on Oh, I see. Interesting.
All right. So for 5 minutes connected, brilliant. Connecting. Initializing. Perfect timing. All right, so there's my x, right? I've got this x dot requires grad equals true. Well, x dot requires grad. What's it going to be?
Now it's going to be false.
It's going to be false by default. Yeah. So if you create anything, it will not be something that PyTorch thinks you are looking to find the gradients of. Now, if I can of course set that equal to true, and then if I were to print that, it would say that it's true. So we'll save that for the moment. So just remember it's false by default. So let's say that loss is equal to x plus. Let's do a proper one. Let's say it's equal to We've got some y, so y is equal to wx plus b. Plus b, I'll need those w and x. So w is torch dot random. Is that a method? And then b is also equal to that. I think I've got to specify the size. We'll see what error it gives me. Cool. Module object is not callable. Torch.random.random.
Random with random.
Thank you. Yeah, let's do rand n, so we just get a number from a random normal distribution.
Oh, it's because your session has reinitialized, so I think you have to call torch again.
Torch.random, let's just look it up. Torch.rand, somewhere in between where we were. All right, so torch dot does that work? Let's just get it right. All right, it says something funny's going on. Okay, it says received an invalid combination of arguments, got empty tuple, expected a tuple of integer size. So I've got to specify the size. I'm going to have a one weight and one bias, like that. Okay, I run this. Now it says both arguments to mapmol need to be at least 1D, but they are 1D and 0D. Let's print their shape. I'll comment out the other stuff so we can move a little bit faster. W.shape, it has this shape of 1. What about x? Has this shape of 0, apparently. It's just a scalar value. So I want to create a torch tensor. Let's create it from a list of numbers. 1, 2, 3, like that. So now it's going to have 3 numbers in. It has torch size 3. I want to bring back this, but now my weights are going to need to be 3 values. Assuming this is just a single example, then I should have 3 weights like that. Can I multiply them together? I expected them to have the same data type, but found float and long. That's a problem. The problem is that when you create a tensor from integer values, it turns it into a long data type, which is like a 64-bit number. Not a really important detail. The important thing is the fix, which is just to put them as decimals. Okay, so there we've got now everything seemed to work. My b, I'm going to say it's a random number there, and then we will print the y. Okay, cool. So that's the calculation so far. 2 random parameters. None of them have requires grad equal true, and I've calculated this output y. Print y dot requires grad equals true. Sorry, print y dot requires grad. It says I spelled it wrong. It is, of course, false by default. Now, let's imagine we've got this loss. So the loss is going to be the difference between the label and the prediction. So the label I'm going to say is value 1, PyTorch integer, sorry, Python integer. And when I combine that integer with any PyTorch tensor, the result is also going to be a tensor, because the tensor needs to track where did it come from. It came from this addition. So the loss here is going to be the difference between these two things squared. So it's the mean squared error loss. I've only got one example here, so I won't do the mean, but we'll just do the label minus the prediction squared. Again, I don't need to use any fancy PyTorch square or anything. I can just use the Python stuff. And under the hood, PyTorch has defined how this all works. So if I calculate the loss and print the loss, comment all this stuff out, and then run that. Now I've got this loss value, okay? So here, of course, this is also going to have requires grad false. If I do this, it's going to become true because it's calculated from the from a value which requires grad equal true. And you see now it has a grad function. This has appeared because it must now track where it came from, because I need to know how to figure out this thing's gradient, because I'm going to use it to calculate all the other gradients. And then from there, what else do we have? Now, if we do loss.backward, what that will do is populate the gradients of everything that has requires grad equal true. So I don't actually want x dot requires grad equal true, do I? I probably want w. That's more realistic. That's the kind of thing I want the gradient for, because that's the thing I can change and roll down the hill for. So I'll put that down down below where I've defined w just there.
Keyboard shortcut for what you just did.
This one.
Yeah.
Option up down. Yeah, please keep asking. I'll give you all gold star for shortcuts. So if before we do loss.backward we print w.grad, what's it gonna be? Not true. Anybody else? What's the grad gonna be? The grad is gonna be nothing yet. It doesn't exist yet. If we print it after we've called backward, it should be populated. So you can see there, firstly it's none, and then you call dot backward on something which was created from this w, and now w has a dot grad.
Populate the gradient of all preceding.
Exactly.
variables.
That's exactly right. Yeah. So that is it's the graph I showed earlier. Yeah, it populates everything in between that requires grad equal true.
So tensors are just like spicy matrices which just track what you've done effectively?
Yeah, it's a generalization of a matrix. So you can have a scalar, a vector, a matrix. If it has more than two axes, it's a tensor, whether it has 4 or 100 or anything else.
Okay.
It's basically just a collection, a cubic, or kind of, what do you call it, like a rectangular collection of numbers,
Yeah.
basically. That's what the
Okay.
tensor is. Sweet. So now we've got this dot grad. What else did we have? Requires grad equal true. Grad function, maybe. So if we look at the grad function now, you can see now it's something different. Now it says pow backward 0. Again, I don't know what that means quite, but it's to do with the power. It's due to the fact that it came from this calculation. So again, the tensor is tracked where it came from. And at the end of this, you can see now it knows how to calculate its own gradient, which is what it did when we called dot backward. There's a lot of detail here, and a lot of this will be covered up under the hood once we get to the end of this lesson. So to move on from that, I now want to talk about, firstly, one thing that's really important is whenever you have data in PyTorch, just remember this rule. The first dimension is the batch dimension. So up here, when I created this x here, I was very badly behaved because that's just a vector, and I said it was one example. It really should have brackets all the way around the edge, like that, because this thing could contain many examples. And that's usually the format your data comes in, where each row is a different example, and each column is a different feature. But the first dimension, always the first dimension, that's the one with the different rows. That's the one with the different examples are. That's what we call the batch dimension. Each example in the batch is in the first dimension. And then within that, you have the example itself. So here, the first dimension in this one's a simple matrix. First dimension is obviously the rows. So the rows contain different examples. The columns contain different features of those examples. Great, so that's one thing to remember, right? Just want like key rule. Key rule, the batch dimension is the first dimension. So if you see some data, it's got a lot of rows, it's either the labels or the features, you know that the first dimension represents how many items there are in the batch. If you take its length, that's how many items you have in your data set. We'll look at data loaders in more detail as we go forward, but a data loader does two important things. It chunks up your data set into small batches, and it shuffles them. These are the batches that we're actually going to make predictions for, calculate the loss, calculate the gradients, and then update the model for before we do that all again, repeatedly. And I'm going to use it now, run that cell to define it, to show you the whole training loop from end to end, which should tie all of this together. The only missing ingredient right now is the optimizer. So in PyTorch, again, it's got a load of useful, very complicated mathematical things you can pull straight off the shelf. Like all the transformations, like the optimizers. Stochastic gradient descent, haven't talked about it much. There are many more complicated optimizers, like Adam is another popular one, and it's not really worth even wasting your time understanding how they work so deeply, other than to understand that they do gradient descent, if you want to get to just the essence of this, that is. So you can pull them straight off the shelf and use them very easily with PyTorch. This is how you do it. You go into the optim module in Torch, and you get whatever optimizer you need. That's a class. You can tell because it starts with a capital letter, capital S. In this case, they're all capitals, but that's just a coincidence. And then you pass it two things. You pass it, firstly, what parameters do you want this optimizer to optimize? And thanks to torch.nn.module, which every model inherits from, that module has a parameters attribute. And that parameters attribute returns you all the parameters in the format which the optimizer knows how to take them on as an argument and use them later. It's going to optimize those things which you pass in as the first argument. And the second thing is the learning rate, which controls the step size of the parameter updates when we roll down that hill. Again, don't want to go into gradient descent here. Check out in the check out in the machine learning essentials pathway. So define that. Now we've got an optimizer. And here, quick example before we put the whole thing together. This is really, this is like how you use the optimizer. There's one important thing that I'll show here, which is the .step method. The .step method, that is for actually making the parameter updates. So after we've initialized a model, initialized an optimizer, made some predictions using the model, and then probably calculated their loss and done loss.backward. Now, the .grad attribute of all of the tensors, all the parameters in the model, they're populated. The .grad attribute of all of these things exists. And so that is the thing which the optimizer needs to know, like, how should I update this? Which direction's downhill, basically. So once you know that, you can do optimizer.step. And what that does, depending on which optimizer you're using, is under the hood, it just runs one iteration of the update function. Takes the parameter's current value, moves it a little bit in the direction downhill. In the simplest case, that's in the case of stochastic gradient descent. So that's how you make the updates. If we do all of this in a loop, then you've got the training loop. And once you can build that, you can, well, that's the generic thing which happens for pretty much any model. Whether it's something very complicated like a GPT, or whether it's something very trivial like our PyTorch linear regression here. You want to run the training loop to just iteratively update the parameters. So I'll leave you guys to dive into that later, but I will I'll implement all of this from scratch just to show you what the training loop looks like from end to end. So a lot of times, if you want to train these things, you're going to write a function like this. I've called it train, and it takes in the model and the data loader. First thing I'm going to do is basically I'm going to say, well, I want to go through the data set. I want to go through the data a lot of times. I want to make a lot of updates to my model, and I'm going to do that little chunk of data at a time. But maybe I don't have a very big data set, or maybe I need to make more updates than I have batches in my data set. So I'm going to go through the whole data set many times, right? And we call one round through the whole data set an epoch. So I'm going to say for each epoch in my range of epochs, I'm going to go through the data set that many times, essentially. And then I'm going to go through each batch. So I'll say for batch in data loader. Remember, we'll cover this in more detail later, but the data loader does two things. It batches the examples together into, it batches the data set together into little batches, and it shuffles them every time it restarts. So I'm going to go through the data set this many times, and I'm going to go through every batch in the data set. For each of them, what am I going to do? Somebody fill me in with some of the steps here, the stuff that we've talked about so far. I've got a batch. Yes, sir. Exactly, yeah. Firstly, we need to separate out the features and the labels, which are in the batch, like that. And then, exactly right, we're going to pass the features through the model. What does that give us?
Gives us on the weighted model the gradient of which weights.
This doesn't give you the gradient.
Prediction.
This gives you the prediction. Yeah, thanks, Dalia. Good teamwork. So prediction comes out of the model when it's called on the features like that. This here is just the same as saying features equals batch 0 and labels equals batch 1, because the batch contains those two things. So step 1, unpack the batch. Step 2, make a prediction. Step 3, anybody? Calculate the gradient. Exactly. Yeah, how do I do that? What function? Dot backward, exactly. So loss dot backward. Like that. What does that do? Somebody give it to me in a nice one sentence.
Know where to.
Yeah, yeah. What attribute does it populate of what? What was that?
I was saying the fastest.
It. Yeah, maybe, but specifically it updates what parameter? Did I hear it over here? It sets the dot grad, exactly, yeah, a bunch of people got it at the same time there, yeah. So it sets the dot grad of what? In general, all the model parameters, yeah. In this case, the weights and the biases. So we may have models later with many more parameters. They'll all be generally weights and biases, but it sets all of their dot grad attribute. Question? We definitely need to do that, yeah, thank you. So loss is equal to, again, you can pull it straight off the shelf from PyTorch, torch.nn.functional.msc loss. Take the mean squared error loss between the prediction and the labels, like that. Again, just look it up if you don't happen to know it like I do. And then do loss dot backward. After that, next step. Now we've got the loss. What happens next?
We want to update our parameters.
Yeah, we want to update the
based on
parameters.
Some kind of optimization strategy.
Exactly. So we need to do something up here and then take that step. Up here, I need to define the optimizer. And that comes from, as we saw, torch.optim.sgd. So get that optimizer, the SGD optimizer, is just going to roll the ball down the hill in maybe a rather sophisticated way. And it takes in two parameters. Anybody remember what they are? What?
Learning rate.
The learning rate is the second parameter, exactly. I'll just initialize it as a random small number. Anybody else? The model parameters, yeah. How do I get the model parameters? Model.parameters, exactly, yeah. And that's a method, right? So we need to call that one. So that's us defining the optimizer there. We give the model everything that it needs to optimize. And then down here, we need to use that optimizer. How do I use the optimizer? Somebody from this side. Exactly. Optimizer.step. That just makes one update of the model parameters of everything the optimizer is tracking. You can set that to whatever you want. Sorry. Exactly. We need to zero the gradient. So right now, at this point, the model parameters have had their .grad attribute set. Their gradient tells you which direction to go. And we've made an optimization step which changed those model parameters. But they still got the old .grad attribute. It's stale now. It shouldn't be there because it tells you how steeply the loss changes at an old parameterization, not the current parameterization. So that's why you need to do optimizer.step. .zero grad. And that will reset it back to none for every parameter, again, tracked by the optimizer that's passed in here. Is there anything else that needs to happen? No, I think we're good, right? So if you understand that, you understand the learning in machine learning. And that extends to deep learning all the way to GPT, okay? That's it. If you get those steps, really it's these key 5 lines there, which are make a prediction, calculate how bad it is with the loss, find out how the loss changes with each of the parameters by doing loss dot backward, calculate the gradients, make an update using those gradients, and then just reset the gradients back to 0. So with that, we're gonna wrap up early now, and we'll leave it here today. So I want you guys to dive into that notebook and make sure you're comfortable with all of that. We're going to be using everything we've covered today throughout the rest of the series. Have a go at the practicals and get hands-on with everything there. And we'll link back up here tomorrow. Okay? How do we get the final output? You're talking about the final model, or? Yeah. So there's a notebook called Saving and Loading Models. You can use that if you want. But essentially, at the end of this, you've got a trained model. So here, you can use the model. You can do model.save, something like that, and or something along those lines. Anyway, you get what I'm saying. You could save the model, and then you could load it back in another file, and then you would just call it on new data, something like that. Make sense? Cool. Good stuff. All right, great. Early finish today, guys. We've got another engagement, so we have to oblige to that. But I hope that's helpful. Any questions, come and grab me now. Otherwise, I really look forward to seeing you all tomorrow. Hey, what's up? How you doing? This one.
Yeah, thank you.
Great one. I should have mentioned this. So it's called misconception. It doesn't reset it, it adds to it. It can be useful in some cases, but what it does is it accumulates. Yeah. Okay. So if you mix up the 0 graphs, you get this other thing where you get the old continue. Yeah, exactly. Like the update, you can have less and less information because the gradient fills all the same value, and that becomes more and more value for it. So you need to do 0 graph. Yeah. So I think one example would be, let's say. Let me look up. It might be something like where you you've got a model and it predicts 2 things at the same time. It predicts the object detection and object classification. You want to optimize both of them. So you've got this like dual target. So you want to get to the end of one and do dot backwards. Get to the end of the other and do dot backwards, and then just do one optimization. So that's the kind of relation we're using. I'll look them up. I'll build my book. Yeah.
There's a call 0 graph
Let me just grab these guys out because I gave you a stunned look earlier in the lecture when you were talking. I just want to say it's good to Cool. Right. Hope let's see around every hour. Thanks. Yeah. Oh yeah. So you need to sign up. Do you have a sign up? Register series. You don't have a view. I'm just wondering if you can try it.
The form to register for this series. Yeah, I have it.
Okay, cool. Yeah. Where is that?
Yeah, I can send you the link on Discord. Are you a student here?
Yeah.
Yeah, yes, I can send you the link.
Cool. Thank you.
Just message me and I'll send it to you privately.
Yeah, that's all.
Thanks, that's my pleasure.
I send you the details.
Awesome.
Yeah, we won't be here tomorrow, but it's
Cool. Great stuff. I hope it was useful.
yeah, really good.
I'll see you soon.
Thanks much.
All right.